Welcome to the fourth and final lecture on representative sets or matroids. We will give you one more example in this lecture about directed k cycle, at least k length cycle, and then tell you what are the generalizations. So, first let us just do a recap of what we have done. So, you are given a universe U, a family F of subsets of U of size P and an integer Q, and you want to produce a set F hat of F which is called Q representative if the following property holds. What is the property holds? That for all B subset of U whose size is Q, if you are able to find a set A in your family such that A intersection B is empty set, then in my subfamily F hat also I should be able to find you a set A prime such that A prime intersection B is phi. Okay? So, these kind of subfamilies are called Q representative because it is able to maintain disjointness property of F in F prime with respect to all sets of size Q. Okay? So, this is why it is called Q representative. It represents F with respect to every Q size set in terms of disjointness. If you give me a set, if you give me a set of size Q, if it was disjoint with respect to some set in the family F, it is disjoint with respect to some other set, maybe the same set, but in the family F hat. So, in the smaller family also I am able to produce a set which is disjoint from the set given. Okay? So, that is what was the notion of Q representative was. And what is the lemma that we proved? We proved that if you look at a minimal family of sets and we define minimal, okay, then there exists a F hat, right, whose size is independent of the size of the inverse. It only depends on the size of sets in my family and the integer Q or the sets with size of the sets with respect to which we are trying to call representativeness. Okay? And that was P plus Q choose pi. And further, we also talked about computation, that there is an algorithm which can compute these things in P plus Q to the power Q if big O of 1. Okay? There are, as I said, there are much faster algorithm for these problems and they can run in time 2 to the power big O of P plus Q, little o of P plus Q. Okay? So, there are algorithms with these running times and they are the ones which are used to give faster and faster algorithms for some of these objects. So, one interesting cute application that I would like to talk about in today's lecture is about directed k cycle. So, let us try to understand what is directed k cycle. Okay. So, input is going to consist of a directed graph G, positive integer k, parameter is going to be k, and the question is, does G has a directed cycle of length at least k. Okay. Notice that, so why the question is much more interesting, that it could be that we do not have cycles of length k, k plus 1, k plus 2 dot dot dot, but maybe directly has a Ham cycle, right. But all we are saying to you that look, so if you had a cycle of length k or k plus 1 or this, in this case we could have applied color coding or any other approach. Okay. So, in that sense this question is very different, right. So, that G has a directed cycle of length at least k, right. So, we want to test whether, so it is possible that graph does not have a cycle of length any function of k, but but it has a much larger cycle. How can I find such a cycle? Right? It is not even obvious. Okay? It is not even obvious that we can design n to the power f of k algorithm for this problem. You may ask, okay, why directed graph? If the way the conditions are, why not ask this question? Why not ask this question on undirected graph? Valid question? Yes, this question makes sense even on undirected graph, but for undirected graph, there is a cute trick. Okay, there is a cute trick that is able to solve this problem. Using repeated application of color coding. Okay, I would tell you that you wait, you pause the video and then think for a few minutes before looking at what I did, what I do next. Okay, so the algorithm is very simple for this. For undirected graph, the algorithm is first. The algorithm is first very simple. Is that, look, we check cycles of length k plus 1 up to 2 to k. Okay? Just check whether do we have a cycle of length between this using color coding algorithm. And this is going to take you some 2 to the power big of k n to the power big of 1 time. Okay? Done. So, if you succeed, great. Okay. Else, what you do? Arbitrarily contract an edge. Okay. So, you pick up an edge and contract. So, what is a contraction means? So, contraction means basically if you have two vertex and edge u v, okay, you make a single vertex u v, okay, and make everybody which was adjacent to u, you make adjacent to u v. So, this is what contraction means. Now, let us look at G contracted u v. This is a symbol that we have. Now, I claim to you that if G contracted u v, okay, rather let us say, okay, if G has a cycle of length at least greater than 2 k, then G contracted u b has a cycle of length greater than or equal to k. Why? So, let us prove this. Okay. So, if G has a cycle of length at least 2 k, so here is a cycle. Okay. It is possible that we have not contracted any. If we just contract an edge on this cycle, then that is great. I mean, there is nothing to worry, this cycle will survive. If we contract an edge completely outside on this cycle, nothing will happen, this cycle will survive. What I mean by this, if you contract this edge, the length of the cycle is then like 2k, at least 2k. So, now you have greater than 2k, so which is like still more than k. And similarly, if outside nothing will happen, if you contract and nothing will happen, the problem could be that I could have a chord, right. I could have a chord like this. Say this is u and v. Now, if you contract uv, what will happen? If you contract uv, notice either this part of the cycle or black part of the cycle, right? So, now you will get two cycles, right? If you contract uv, you will get a cycle starting at u, ending at v, and there is another cycle, the blue cycle is starting at u and ending at v, because how the picture will look like? It will become uv identified and a black cycle, a blue cycle, okay? And because both together their length was like more than 2k, either the black cycle has length greater than or equal to k, or blue cycle has length greater. So, now you have shown that if G has a cycle of length at least 2k, then G minus uv has a cycle of length at least k. Great. But what more we do? If G contracted uv has a cycle of length greater than k, then G has a cycle of length greater than or equal to. Why? Because look at this cycle in G minus uv. Okay. If uv is not on the cycle, then this is also a cycle in G. Okay. And now, suppose uv is there in the cycle. Okay. But then what do you know about uv? uv is an edge, right? uv is an edge, right? And what do you know? This is a neighbor of, okay, this is a, okay. So, now let us look at this case. Okay. So, look at x, y and uv. Okay. Now, okay, on this cycle, first case, x is a neighbor of, x is in the neighbor of u, y is also neighbor of u, x is a neighbor of u, okay, y is a neighbor of v. This is one possibility. Okay. X is a neighbor of v, y is a neighbor of u, x is a neighbor of v, y is a neighbor of v. These are the four possibilities. Now, if x is a neighbor of u and y is a neighbor of u, replace uv with u and then you get a cycle in G, okay, in this case. And x is in the neighbor of u and y is in the neighbor of v, then you just, then you take x, you have this edge and then y. So, cycle length would not have shrunk, okay. And similarly here. So, the matter of fact is, okay, so the moral of the story is, that we do have a cycle of length at least k. Okay. What did we gain? Number of edges in G decreased. Okay. So, it is like a one-way function. Okay. Okay. So, by repeating this operation, we can achieve 2 to the power big O of k n to the power big O of 1 time algorithm for testing whether G undirected contains a cycle of length at least k or not, contains a cycle of length at least k or not. Okay. So, that is it. So, this is for the undirected graph. Okay, but okay, good thing, or rather I would say, think why this does not work for directed graph. Okay. Secondly, what possible structure we could find to contract to imitate or to imitate the above algorithm. Okay. So, we took a digression and I told you a little bit slightly interesting algorithm. This is like more like a puzzle for undirected graph, but it is a puzzle which is worth to know. Okay. Okay. So, now we go back to the setting of directed at least k cycle case. Okay. So, we have gone back to okay. Now, let us try to. So, one simple observation or the lemma that will at least get us started, and that is like a starting point for some of these algorithms. The basic lemma is G has a cycle C, okay, on at least k vertices, okay, at least k vertices, if and only if there exists vertices u comma b, a simple path p1 from u to v on exactly k vertices, okay, and a simple path from v to u, okay, such that if you look at the intersection is basically u comma v. Okay. What this tells us? That look, the lemma says us, proof is much simpler than the statement, that if you G has a cycle on at least k vertices, then we can find the following thing. What is the following thing? I can find there exists some vertex u and v, okay. I can find some vertex u and v and a simple path, and this contains exactly k vertices, and this is what I call P1, okay, and I can also find a path from v to u and a simple path from v to u, some another simple path from v to u, okay, call that P2 path, I should have called it P2 from v to u. So, let us, okay. So, there is a simple path from P2 from v to u, and what is the property of this path? The intersection of these two is only at v to u. So, this is, okay. So, this will imply a directed cycle of length. Okay. Why is this true? The proof is very simple. You pick up a cycle. So, this is your C, okay. Pick up the first k vertices. This is exactly first, this length is k vertices, okay, u to v, call that P1, okay, and take this part of the path as P2, right, that is it. Okay, this is your P1 and this is your P2, that is it. So, if we have a cycle, we can find such a path, okay, and the backward direction is also obvious, right. you look at a path u to v, this is your p1 has length k, and there is another path v to u, right, which could be just an edge actually, by the way, that could just be an edge, but still you are able to close a cycle and the length of this cycle is at least k. Okay? So, this is it. Now, notice that this lemma tells us a simple XP algorithm at least. Okay? It provides, what is that? So, what it tells us that, look, basically it tells us that for all uv and path of length k between them, say p. So, you enumerate all the path, I have enumerated, okay, does not matter, there is a path on this. Now, what will you do? You look at G minus internal vertices. So, you look at, basically you look at G minus Vp, okay, all the path, but Vp minus u comma v. So, basically this is a, okay. Now, in this graph, find a path from v to u, that is it, sorry, yeah, from v to u, find it. So, now you know by definition this is a path which is disjoint from all the internal vertices of path p, and this will act as a p2. So, if you for any uv, if you are and a for any uv and any p, if you are able to do this, you can concatenate this and say that there is a cycle of length at least k, okay, and find a path from v to a p, that is it, find a path. I mean, I am not saying just find the shortest path, okay, for all that you care, okay, because this can be done in polytype. So, this step can be done in polytype, and how many choices of uv we have? So, the total number of choices of uv we have is like n square. How many choices of internal vertices we have is like n minus 2, k minus 2, okay, and I need to test whether there is a path between them or not. So, that is going to take 2 to the power k time, check whether this u, v and this k minus 2 vertices, right. So, this is the time, running time for this person, and for each of them I need to find p path which is like polynomial time. So, in total this is like roughly n to the power big O of k time. So, we are able to design an XP algorithm, okay. We are able to design an XP algorithm for directed at least k path flow, okay. But this is not what we want to do, okay. So, now let us try to take this algorithm, okay. Okay. So, our algorithm is very simple, okay. Let us recall we have uv, okay. So, what is we did? So, let us call this p u v k, all the sets x, okay, mod x equal to k, let us say not k, but like just so that we recall the definition, p mod x equal to p, there is a uv path directed, okay, in graph induced on x of length p, or yeah, okay, or you can say visiting all vertices of x, okay. So, this is right, and what we did here, we try to enumerate p k u v, okay. Natural question, do we need to enumerate all? Okay. So the point is, look at UV. Okay. Look at set pk UV. If I knew that this directed cycle has length, look at this directed cycle. I said, look, if I knew that this has some length L, the red part, then what I could do, that I could compute pkuv. Okay, I could compute, let's say, uv hat. Okay, rather, let's say, pk uv. I would have computed pk uv hat, which is a representative, but it is representative with respect to L. So what is the meaning of this? I say, look, so if I would have computed this, then what would have kept? What would have done? So for every uv, I compute p hat q k uv, which is an L representative for this. It means it would have meant that I have kept some family of sets between u and v, that look, you give me any L length path, and that's a set for which I have something which is disjoint, then I have something which is disjoint in my set also, meaning, which will mean that suppose you would have given, so basically what it means, that you look at any L length cycle and suppose this is some set Q, okay, and I know that suppose this is P. So P is inside this and P and Q are disjoint. Now because of the representativeness, we would have found some P prime here, so that P prime intersection Q is disjoint, okay, and P prime concatenated with Q will give us cycle of length greater than or equal to K. But the problem is, we do not know whether L could be function of K, right? K could be, L could be much larger, and if L is going to be much larger, then the computation of this representative set is going to be, it depends, what was the computation of this representative set? So the representative set computation, if you remember, was P plus Q, or rather, okay, so this is fine. So it was P to the power Q, where Q was the future or the set from the future. So now P is like K, it will be like L. So this is an algorithm we cannot afford. Okay, so yes, we need not enumerate every path, but it depends on the length L. Okay, so this almost worked, but did not work. So almost worked, but it did not work. Okay, so we will fix it. We will say, well, we'll prove L equal to K is good enough. Okay, or rather 2K is good enough. In a minute, we'll prove that. Okay, so we'll prove a lemma which is analogous to this lemma, but that will be at the heart of our proof. Okay, so our central lemma is, this is a combinatorial lemma, this is not very hard, but the heart of the proof of this algorithm is the following simple combinatorial lemma. What is this? If there exists a cycle C on at least k vertices, okay, on at least then there exist two vertices as before, u and v, okay, and a path p1 such that, this is important, where, and a path p1 such that vertex set of p1 is an element of, it's a representative set one second. Okay. Okay. Is a representative of, so it's a Q representative, okay, okay, of P U V Q. Okay. So if you look at a path of length k, okay, okay. So this is a representative of this, where what is the value of q? And q is less than equal to k. Okay, and there exists a path P2 from V to U, okay, with vertex set of P1 intersection vertex set of P2 is equal to U comma V. Okay. So basically, it's a truncated version, or it's a, basically you can think of this as a representative set version of the earlier lemma, right. What I am saying, that I will find you a vertex u and v such that I will tell you that I will compute a q representative, q is at most k, such that, like, so what I am saying, that rather than enumerating path from everything, I will enumerate path from my set, okay, and then there exists other path from V to U which is disjoint from him. Okay. So now suppose Q is k. So what is the size of this? Notice, so every path, so look at P U V k. Okay. So this is a set, I mean, and we computed another q representative for this. And what did we computed? We computed P U V k hat, and we computed another k representative for this. Okay. Suppose we did this. Then the size of this is going to be how much? P U V k hat, it is going to be, the size of this is going to be at most 4 to the power k, right, because P plus Q, choose P. So P plus Q, choose P, which is in our case, what is P? The lengths of paths here. So, or the lengths of paths here, which is key. And what is Q? The sets of vertices with respect to which I want disjointness cardinality of the sets of set, which is again k. So this is k. So this 2k, choose k, which is at most 4k. Okay. So this is at most 4k such, 4k such. So the algorithm is very simple after this, right? Enumerate sets in fix UV, enumerate sets in PKUV hat, this is P1, check if path exists in G minus VP1 minus U comma V. There exists a path from V to U in this. If there exists a path, that will act as a P2, right? And that's a path of length at least k. So the algorithm is what is the running time of algorithm? Time to construct P U V k hat P U V k for all U comma V, okay. And so with our algorithm, we know how to compute this by doing the same way the way we did for k paths. You start with one vertex and do all these things and computing k representative. So you can compute this representative in time k to the power 2k actually, because this is a length of k. So in the beginning, like you have to vary. So when you start with one vertex, you will compute 2k representative. So yeah, so roughly this will take you k to the power big O of k time, n to the power big O of 1 time. So this is fine. You can compute all of them, and now you have to go through all 4 to the power k sets in this and run in a poly time. Okay, so the total time is k to the power big O of k, n to the power big O of 1. And if you apply the faster known construction, then you would have got 2 to the power big O of k, n to the power big O of 1. Okay, and there are also that you can optimize. So if you look at the textbook, it provides you this algorithm. Okay, in the textbook. Okay, good. So it all boils down to proving this nice combinatorial lemma. So let's try to prove this combinatorial lemma, and once we have proved this, algorithm just follows. Okay, so let's just focus on this lemma. Okay, so let's try to prove this lemma. Proof is fairly simple. Okay. Okay, so prove that this is a cute proof. Let C be a shortest cycle among all cycles of length at least k. Okay, so there could be many cycles of length at least k, right? Suppose there are C1, C2, CQ, all these are cycles of length at least k. Okay, among them I pick a C whose size is minimum. Okay, so every cycle in this set has length at least k. I pick the one which has a minimum size. There could be many such cycles of minimum size. I pick one. Okay, so this is what I mean. Let C be a shortest cycle among all cycles of length at least k. Okay. Okay, so this is an intuitive proof. Okay. Okay, so you just let's write down the vertices of this cycle. So suppose C is V1, V2, VR. Okay. Okay. Okay, and now let P1 prime be V1, V2, Vk plus 1. And now I define B equal to, this is an important, is Vk plus 1 to V2k, okay, if R is greater than or equal to 2k. Vk plus 1, Vk or Vr if R is less than or equal. So, what I have did, I said look, here is my cycle, here is my cycle, and here is my cycle. Suppose this is V1 to Vk on this. Okay. Now, I look at the length of this cycle. Okay, this is what. So, I say look, is, and suppose this is my Vr, okay, Vr minus 1, Vk plus 1. I say look, if this cycle is, this part of the cycle is here, okay, I check. So, I am going to form a set B. If R is less than 2k, then my B is everything. Okay, then in that case, my B is everything. Otherwise, what I am saying to you is that, okay, fine. Okay. So, this is B when R is less than, R is strictly less than 2k. Okay. R is strictly less than. Okay. Now, imagine that R is greater than 2k, but it could be much more. In that case, I start with Vk plus 1 and I go and I stop. This is my B. Okay. And what is the property of this? This is nothing but V2k. So, I do not go further. All I go at this point of time is first next k vertices after Vk. Okay. So, this is how we have constructed our B. Okay. Now, we will have two cases. Okay. Look at two cases. Look at the first case. What is the first case? Suppose R is less than 2k. So, this is my R is at most 2k. Okay. Now, what have I computed? What have I computed? Okay. Now, let us look at P V1 Vk. Let us call this V1 U and let us call this V. Okay. Okay. So, now let us consider PUV. Let us consider PUV, okay, k, and the representative we have computed up to length k, which is P UV k. So, what is the meaning of this? The meaning of this set is that if there exists a set B of size k such that there exists a set A in PUVK, such that there exists set A in PUVK such that A intersection B is empty, implies there exists A prime in PUVK such that there exists A prime in PUVK such that what is the property? There exists A prime in PUVK such that there exists A prime in PUVK such that A prime intersection B is phi. That is all the definition of this is. Okay. So, now we are in the case R equal to less than equal to 2k. Okay. So, B is B, and what is our A? A is vertex set of P1. Okay, this is P1. Okay, okay, that the path UB. What I know that A intersection B is empty. Then what will you give me? You will give me another path. Okay, you will give me, no, this is what we call P1 prime. Okay, so what will you give me? Okay, you will give me a set A. Let's not call that vertex set of P1. Okay, and its intersection with B is phi. So now I can find a replacement in this case. Okay, so in this case, okay, okay, so we are talking about this case. Okay, so now look at this. This was U and this is an V. Okay, I can find a replacement. So now I will find another replacement. Maybe not this, but like this. Okay, of length K, but it is still disjoint from the red part. So this is going to constitute a cycle of length at least K in this case. So this is an easy case. So because the cycle was not too long and you have kept this prefixes that, like for every prefix UV, you have kept a prefix that act as a disjointness with respect to any future prospect. So this is perfectly fine. So the not so easy case is when the second case is slightly more, not complicated, but slightly more interesting, let's say. Okay. Okay. So let's look at, so let's look at this case. Okay, this is the case. Now, what you know? You know for sure that there is a replacement here. There is a replacement for P1 prime. Okay, there is a replacement for P1 prime. Okay, there is a replacement for P1 prime, which is okay. In this case, we know there exists. So if you think of this as your A and this, then there exists A prime in P, K, U, V hat of, sorry, my mistake. Which is disjoint from this. Let that A prime, we call it vertex set of P1. Okay. Now, let's morph this picture. How does it will look like? So the picture is going to look like slightly different. Paste. Okay. Now, all I know, okay, this is the same object. Okay. So now, okay, so this, I don't know this path exists or not, but I know that some path could exist like this. Okay. But what is the property of this path? This path property is that VP1 is still disjoint from B. This is an important point. So now let me show you, okay. Okay. Now let's start from V. Okay. Let's start from V. I start from V and let, okay, okay. I think this picture is slightly, I don't, okay. Okay, so let's say this path We don't know if it exists or not, maybe not exist, but there exists some other path which starts at u, okay, and maybe goes around like this and come back. Okay. Okay, and the direction of the path is start here. Oh God, is this? Okay. Now you start from V, you traverse along until you hit first vertex not on B. Okay. So suppose you hit up this vertex, you hit. Let's call that vertex W. Okay. Now, so what is my path? I know that this green path is disjoint from this red path. So now I can construct a path. How will I construct a path? I will follow the green path W to V. So I'm going to start. So I'm going to have my, so look at P1 star as nothing but W to V path, which is green, that is in P1, right? So basically what happens is this is your P1, okay, W is somewhere here. So now we decided to take this path, okay. Now where does it end? It ends at U. And now what do I have? I have another path from U to W, which is of okay, which is of this, right? And starting from U, this is the first vertex that I hit, right? So none of these vertices contains any vertex from P1, okay? What you know, this is length at least k, okay? So what I've been able to show? So we have been able to show that, hey, here is a short cycle whose length is greater than or equal to k, but it is shorter than mod C that we started with. Okay, mod C that we started with, right? So we can show, because look, it definitely does not contain U, like it does not contain this should be V, okay, starting from V. Right? So the path length of P1 was fixed. So each of these paths are like subpaths of their corresponding thing. So call this a C star. What is the property of C star? C star is strictly less than, say, you can check for yourself, and C star is a cycle in G of length at least k. Okay, so this is a contradiction. Okay. So what do we know? So we know now that our statement of the lemma holds, and in particular the shortest cycle of length at least k has the property that you can find vertices u and v and a path P1 in my rep set such that there is a path from V to U which is disjoint. Just find anyone. So that's it. So this should end our lemma as well as the proof. Okay, and what we have shown is that directed k cycle is FPT. In fact, we gave k to the power big of k, n to the power big of 1 time algorithm, and there is much faster c power k n to the power big of 1 time algorithm. Okay. So now let me take another 10 minutes and let me talk about matroids. Okay. So up until now we have talked about set system. Okay. But there is another object of our interest are what is called matroids. So what is a matroids? Matroids is basically it's a universe and a family of set system. What is the property of this? So the first property is it's hereditary. If X belongs to family, then all subsets of X belongs to family, and this is called hereditary property. Okay. Secondly, phi is in my family, like that is empty set is in my family. And thirdly, which is the most important property of matroid, is what is called exchange property. Okay. And what is an exchange property? If there exists X and Y in our family such that mod Y is strictly greater than mod X, there exists Y in Y minus X such that X union Y is in my family, right? So this is what it says, that look, I have a big set Y and I have another set X, cardinality of Y is bigger than X, then I can find an element, okay, rather this is not a picture, right picture. Suppose this is a set X and this is a set Y, and Y is larger than set X, then I will be able to find an element Y here, okay, such that X union Y is in my family, right? So we can enlarge X by an element that is not present in X but only present in Y to my family, okay. So these kind of set families are called matroids, okay. Notice exchange property tells us that each maximal set in family has same size, and these are called rank of a matroid. Okay. Of course, they have a relation to linear algebras. Okay. Okay. So this is one thing. Okay. Another property which is a very right. Let's look at some example of matroids. Okay. So some examples of matroids, one is something called UNK or uniform matroid, okay, which is basically all subsets of size at most k. You can check this from some matroid. Okay. Okay, but there are some very, very non-trivial matroid. Okay, but let's say another one I will tell you from graphic matroid. What is graphic matroid? Look at a graph G. Okay, and this is VG and EG. So your universe is H set of G, and your family is all forests. Okay, all forests of G. show that this forms a matroid. There is something called co-graphic matroid. Okay. What is this? Again, my universe is the edge set of my graph, and my family is all X. X is a subset of EG, okay, and G minus X is connected. Like it's basically those subset of edges whose deletion keeps the graph connected, okay, then these are called co-graphic matroid. So there are various matroid. What about matching? Okay. So let's see, my universe is again edge set and my family is X. X forms a matching. So you can show that if something forms a matching, then all their subsets also forms a matching. But you can show that this is not a matroid, because look at this example. Okay. In my family, I will have this set. Okay. Okay. So, okay. So let's just look at this. What happens? So now there is a, let's say, these are red. So blue and red matching, right? Blue matching, right? Let's call this as A, B, C. Now A and C belongs to my family. B belongs to the family, right? Now let's call this matching M1, let's call it. Definitely cardinality of M1 is more than cardinality of M2, okay? But there is no way I can add an edge in either A or C to B, because that will not form a matching. So matching do not form a matroid. Matching do not form a matroid. Okay. But there are ways to navigate it. So in bipartite graph, you can have, say, set A and B, bipartite graph. So you can come up with my universe as A, and your family is X, subset of X. There exists a matching M that saturates X, meaning you have an X here and you have a matching like this, saturates X. Okay? You can show that this forms a matroid. And this is called transversal matroid. Okay. Another important property of matroid that is useful for us, which we like to know, is the following, something called representation of a matroid. Okay. What is a representation of a matroid? Notice that you are given a U and a family. Like F could be very, very large. So how do you check whether some X belongs to F or not? Okay. And elements in F are called independent sets. Independent sets. Okay. How do you check whether X is an independent or not? So of course you could be given explicitly, but the best, one of the best way to give this is basically is to give a matrix over some field F. So you are given a matrix M, okay, where columns are indexed with elements of U. Okay. The columns are indexed with U, and generally this matrix, you can actually take this matrix size is basically rank times u. And what is the property? Look at, so now this is like if you look at x is in F, if and only if corresponding columns are linearly independent over F. Okay. So, basically what is this matrix tells us? This matrix tells us that, look, if I wanted to test whether my set X is independent or not, I go and look at the corresponding columns and check whether they form independent, they are linearly independent or not over field F. So, this is, so a matroid for which such a matrix exists are called representable matroids. Okay. But for that matter, if you take a matrix itself, okay, and take columns as your universe, and what is your family? All x subset of u, okay, x is linearly independent. Okay. Then this automatically forms a matroid, and this is why the terms like independent sets or the rank is used in the matroid, because it appears that the definition of matroid came from some of this matrix application. Okay. So, why did I talk about all this? So, there is a theorem about representable matroid. What is a representable matroid theorem? Is the following. Okay. So, you can also define a notion of Q representative. Okay. So, you are given U and F, this is a matroid, and now imagine that you are given some family F, some family, let us say Q subset of F. Okay. And what is the property of Q? Each set in Q has size p, and that is more important, and each set A in Q has size p, and A is independent. Okay. A is independent. Okay. A is independent. So, okay, because look, oh, yeah, fine. So, that is independent in the sense that it's, or rather, yeah, fine. Then given an integer q and integer q, we can come up with q hat, which is a representative, q representative of q. Okay. And what is the property of this? Well, for all x, say, or rather for all b, if there exists an A in Q such that A intersection B is phi first, and A union B if in our family implies there exists B, there exists an A prime in, there exists an A prime in Q hat with the property that A prime intersection B is phi, and more importantly, so in some sense this rep sets not only preserves disjointness, it also preserves independence. Okay. And what is known is that given Q, we can compute Q hat, given Q an integer Q, we can compute Q hat in time f p q n to the power b. So, it is like in this time, it is quite, actually it is quite, I will, like maybe I should tell you the running time itself. Okay. So, let me tell you the running time, it is quite efficient. So, you can actually compute in time big O of size of q P plus Q choose P, P to the power omega, where omega is a matrix multiplication, P plus Q choose P, omega minus 1 operations over some GFX. Okay. So, look, I am just giving a overall idea, I am not trying to do everything. Okay. And what will the size of Q hat? Size of Q hat is again going to be P plus Q choose P. And this is basically algebraization of a lemma proved by Lovers, or generalization of Bolova's lemma proved by Lovers in 1970s. Okay. So, all I am trying to tell you that all the things about representative sets can be extended to matroids, representable matroids, and they have found also lots and lots of application in designing parameterized algorithms, but somehow those are slightly more complicated, and in my opinion that's not right place to teach or fit in the first course in parameterized algorithms. So, with that let me take a end, and this was also my last class in this course. So, thank you for listening, and the next class will be taught by Neil, and that class will be about techniques or tools to prove hardness in parameterized algorithms. So, have a good time. Thank you.